The next popular method of clustering that we are going to discuss is partitional clustering. This type of clustering is simply a division of the set of data objects into non-overlapping clusters such that each observation is in exactly one cluster. Partitional clustering models are also referred to as non-hierarchical, as the clusters are all mutually exclusive. One of the most commonly used partitional clustering algorithms is the k-means clustering algorithm. In a nutshell, k-means clustering aims to partition n observations into k clusters, in which each observation belongs to the cluster with the nearest mean. The algorithm works iteratively to re-estimate cluster means each time based on the cluster members. This is done until all observations in a cluster are considered similar and all clusters are sufficiently distinct, as defined by the intra-cluster similarity and the inter-cluster dissimilarity objective functions. Let us look at the following example where k is equal to 3. The algorithm initializes by making any 3 random observations cluster centers. Here, our cluster centers are the green, blue, and red triangles. All observations are then assigned to the closest of the 3 cluster centers, as seen in the third diagram. The mean of each cluster is computed again, taking into account the new observation in that cluster. Observations are reassigned to the closest of these new means, and the process is repeated until the means are no longer changing. The algorithm is very naive in the sense that it can produce any number of clusters regardless of whether k is sensible or not. Ideally, k should produce homogeneous clusters. As previously mentioned, all observations in a cluster should be similar, and all clusters should be sufficiently distinct. K can therefore be optimized by minimizing variability within clusters and maximizing the variability between clusters. One way to do this is using the elbow method. This requires computation of the squared standard error, that is, the sum of the squared distances between each observation and the corresponding cluster mean. A plot of the standard errors or distortion against the corresponding case might look like something like this. The optimal k is identified at the point where this plot has the sharpest bend, hence the name elbow method. In our example, this is where it is equal to 3. Up until this point, we have only discussed clustering. That's not the only scenario in which unsupervised learning has proven to be useful. This method of machine learning has also proven to be useful in dealing with high-dimensional data sets. The problem with very large data sets is that they tend to impose a high computational burden, and often some of the variables in the data do not provide much information. The sensible thing to do is to discard these useless variables. But how do we identify them? Using unsupervised machine learning, we can significantly reduce the number of variables in the data and at the same time maintain a high explanatory power by the remaining variables. One popular method used to do this is called the principal component analysis, or PCA. If we define it technically, principal component analysis is a statistical method based on eigenvector analysis. This is a dimension reduction tool that can be used to reduce a large set of possibly correlated variables to a smaller set of linearly uncorrelated variables that still contain most of the information in the larger set. The smaller set of variables are referred to as principal components. To put it simply, this method finds the combination of variables that is able to capture strong patterns and explain most of the variation in large data sets. Suppose our data set contains 500 variables. The resulting principal components will have varying degrees of explanatory power. The first might explain 30% of the variability, the second 19%, the third 11%, and so on. Whereas some may not explain any variability at all. If PCA reveals that 95% of the variation can be explained by 120 principal components, any variable that is not part of those principal components can be excluded from our analysis. PCA is mostly used as a tool in explanatory data analysis and for making predictive models. The most common way in which PCA is done is by eigenvalue decomposition of the covariance matrix, whereby the matrix is represented in terms of its eigenvalues and eigenvectors. To sum things up, we have learned that unsupervised machine learning is good for data where we have no labels associated with them. Observations can be clustered either hierarchically, using hierarchical clustering, or by their proximity to a cluster average, using partitional clustering. Unsupervised learning can also be used to reduce the size of large data sets by identifying principal components, allowing us to discard any variables with no explanatory power. So now we have learned how machine learning algorithms can be used to help banks understand their customers better, and how they can help us to reduce large data sets down to a more manageable part. But there are many more applications, and so far we have only covered the unsupervised learning algorithms. Next, we will turn to supervised learning.